Download this code from codegive.com, link in the description below. OK, let's dive deep into the concept of reentrancy in the context of concurrent programming, particularly relevant to ECE 459 or similar courses. We'll cover the theory, potential pitfalls, and, most importantly, practical code examples with explanations. ECE 459, Reentrancy, Lecture 10, Comprehensive Tutorial. 1. Introduction. What is reentrancy? Reentrancy, in the context of concurrent programming, threads, interrupts, signals, etc., refers to the ability of a function or code section to be safely called again while it is already in the middle of executing, being entered already. This happens when an interrupt, signal, or another thread interrupts the execution of the original function call and then invokes that same function again, either directly or indirectly. Think of it like this: you're baking a cake, the function. Suddenly, the phone rings, an interrupt, and it's your friend needing your cake recipe. You drop the cake batter, interrupt handler calls the same bake cake recipe. If you're not careful, the code is not reentrant, you might end up mixing parts of your original cake batter with the information you're giving your friend, causing a mess. Why is reentrancy important? Concurrency safety in multi-threaded or interrupt-driven systems, ensuring reentrancy is crucial for preventing data corruption, deadlocks, and unpredictable behavior. Interrupt handlers must always be reentrant because they can interrupt any other code running on the system. Signal handlers face similar reentrancy requirements. Multitasking / real-time systems in systems where tasks can be preempted, reentrancy is vital for ensuring correct program execution. 2. The problem: non-reentrant code. Code is not reentrant if it uses shared resources, global variables, static variables, shared memory, or file handles, in a way that is not properly synchronized or protected. The following scenarios make code non-reentrant. Unprotected global variables. If a function modifies a global variable, and it can be interrupted and called again before it's finished, the global variable's state can be corrupted. Unprotected static variables. Similar to global variables, static variables, local to a function but retain their value between calls, can cause problems. Unprotected shared memory. If multiple threads or processes access shared memory regions without proper synchronization mechanisms, locks, semaphores, data corruption can occur. Using malloc and free without protection. Malloc and free often use internal global data structures to manage memory allocation. If these data structures are not protected by locks, concurrent calls to malloc or free can corrupt the heap. Functions that call other non-reentrant functions. If a function A calls a non-reentrant function B, then A itself becomes non-reentrant. 3. Making code reentrant, techniques. The key to making code reentrant is to eliminate or protect the shared mutable state. Here are the main approaches. Avoid shared mutable state. This is the most reliable approach. If possible, rewrite the code to avoid using global variables, static variables, or shared memory. Pass all necessary data as arguments to the function. Copy data to local variables. If a function needs to use a global or static variable, make a local copy of the variable at the beginning of the function, operate on the local copy, and then, carefully, update the global/static variable at the end, protecting the update with a lock. However, this introduces the risk of stale data if the global/static variable changes between the time you copy it and the time you write back. Use locks. Mutexes protect access to shared resources with locks. Mutexes acquire the lock before accessing the resource, and release the lock after finishing. This prevents concurrent access and ensures mutual exclusion. Careful lock management is critical to avoid deadlocks. Atomic operations use atomic operations, provided by the compiler or the operating system, to perform simple operations on shared variables without requiring explicit locking. Atomic operations are guaranteed to be indivisible. This is only suitable for very simple operations like incrementing or decrementing a counter. Reentrant libraries use libraries that are designed to be reentrant. Many standard libraries have reentrant alternatives, example strtoc_r instead of strtoc. Always consult the documentation. Thread local storage use thread local storage to create a separate copy of a variable for each thread. This eliminates the need for locks. This is often a good solution for thread-specific data. Disabling interrupts, very limited use in some very specific cases. You can disable interrupts before accessing a shared resource and re-enable them afterward. This is generally a bad idea because it can significantly impact system responsiveness. It should only be used as a last resort and only for very short critical sections. This is not suitable for multi-threaded applications. 4. Code examples, illustrating reentrancy and non-reentrancy. Let's look at some C code examples to demonstrate the concepts. Example 1. Non-reentrant function, using a global variable. Explanation this code creates two threads. Each thread calls increment_counter, which increments the global variable global_counter. Because there's no synchronization, both threads can access global_counter simultaneously. Problem imagine the following scenario. One thread 1 enters increment_counter, sleep, 1, is called, and it pauses its execution. Thread 2 enters increment_counter, sleep, 1, is called, and it pauses its execution. Thread 1 sleep finishes, it reads the value of global_counter, which might still be 0. Thread 1 increments the value and prints counter, 1. Thread 2 sleep finishes, it reads the value of global_counter, which might still be 0. Thread 2 increments the value and prints counter, 1. The final value of global_counter will be 1 instead of 2. This is a classic race condition caused by the non-reentrant nature of the code. Example 2, reentrant function, using a lock. Explanation this code adds a mutex, counter_mutex, to protect the global_counter. Before accessing or modifying global_counter, a thread must acquire the lock. After finishing, it releases the lock. How it works One thread 1 enters increment_counter, acquires the lock, and starts sleep, 1. Thread 2 enters increment_counter, attempts to acquire the lock, but the lock is already held by thread 1. Thread 2 blocks, waits, until thread 1 releases the lock. Thread 1 sleep finishes, it increments global_counter, prints the value, releases the lock. Thread 2, which was waiting, now acquires the lock, increments global_counter, prints the value, and releases the lock. Result now the final value of global_counter will reliably be 2. The mutex ensures that only one thread can access and modify the counter at a time. Example 3, reentrant function, using thread local storage. Explanation this code uses thread local storage to avoid shared variables altogether. Each thread gets its own private copy of the counter variable. Asterisk how it works asterisk. One thread underscore key underscore create creates a unique key, counter underscore key, that will be used to identify the thread local storage. The second argument, free, is a destructor function that will be called when a thread exits to free the memory associated with the thread local storage. Thread underscore get specific, counter underscore key, retrieves the thread local value associated with the counter underscore key for the current thread. If this is the first time the thread has called the function, the value will be null. 3. If the value is null, memory is allocated using malloc, the counter is initialized to 0, and thread underscore set specific associates the memory address, the counter, with the counter underscore key for that thread only. 4. Each thread now has its own independent copy of the counter. Asterisk result asterisk each thread will have its own counter, and the counter increments independently. This avoids any race conditions. The thread underscore key underscore delete will delete the key, but it does not free the memory that was allocated using thread local storage. That's why the destructor function is set in thread underscore key underscore create. Example 4, non-reentrant standard library function, strtoc, and reentrant alternative, strtoc underscore r. Asterisk explanation asterisk strtoc is not reentrant. It uses a static variable internally to keep track of its position in the string being tokenized. If two threads call strtoc simultaneously, they will interfere with each other's progress. Asterisk strtoc underscore r asterisk the strtoc underscore r function is reentrant. It takes an additional argument, say pr, which is a pointer to hr asterisk. Strtoc underscore r uses the save pr to store its internal state. This allows each thread to have its own independent state. The user provides the storage for this state, the save pr. Asterisk important asterisk in real-world usage, you need to make copies of strings before tokenizing them using strtoc underscore r, because strtoc underscore r modifies the original string. 5. Reentrancy and interrupt handlers. Interrupt handlers must always be reentrant. Interrupts can occur at any time, so an interrupt handler might interrupt code that is already using a shared resource. Asterisk best practice asterisk keep interrupt handlers as short and simple as possible. Delegate complex tasks to a separate thread or task that can be scheduled to run after the interrupt handler has finished. Asterisk disabling interrupts, use with extreme caution. Disabling interrupts can prevent reentrancy problems in interrupt handlers, but it can also negatively impact system responsiveness and potentially lead to missed interrupts. It should only be used for very short critical sections and only if there is no other way to achieve reentrancy. Never disable interrupts for extended periods. Asterisk use spin locks instead of mutexes. Mutexes can block when the mutex is held. Interrupt handlers cannot block. Spin locks busy wait until the lock is available. This is much more suitable for interrupt handlers. Example, illustrative, not fully complete. Asterisk explanation asterisk this example demonstrates a signal handler that increments a shared variable protected by a mutex. This approach can work, but it's not ideal. A safer approach would involve a signal handler setting a flag that a separate thread then processes. Asterisk problems asterisk consider what would happen if the signal interrupts the thread while the thread is holding the mutex. The signal handler would block trying to acquire the same mutex, leading to a deadlock. Interrupt handlers cannot block. Better approach, illustrative. Asterisk explanation asterisk. Asterisk the signal handler only sets an atomic flag, signal underscore received. Atomic operations are guaranteed to be indivisible and don't require locks. Asterisk the thread checks the flag periodically and processes the signal. This avoids any blocking in the signal handler. 6. Common mistakes and pitfalls. Asterisk forgetting to release locks. Asterisk always ensure that you release locks in all possible execution paths, including error handling paths. Otherwise, you risk deadlocks. Asterisk incorrect lock ordering. Asterisk if multiple locks are required, always acquire them in the same order to prevent deadlocks. Asterisk calling non-reentrant functions from reentrant functions. Asterisk this effectively makes the calling function non-reentrant. Asterisk assuming that malloc and free are always safe. Asterisk malloc and free can use internal global data structures that need to be protected by locks. Asterisk ignoring compiler warnings. Asterisk pay close attention to compiler warnings about potential race conditions or thread safety issues. 7. Tools for detecting reentrancy issues. Asterisk thread sanitizer, TSAN, a tool that can detect data races, deadlocks, and other thread safety issues at runtime. It is available in GCC and Clang. Asterisk static analysis tools. Asterisk tools that analyze source code to identify potential concurrency problems. 8. Summary. Reentrancy is a critical concept in concurrent programming. By understanding the potential pitfalls of non-reentrant code and by applying the techniques outlined in this tutorial, avoiding shared mutable state, using locks, atomic operations, thread local storage, and reentrant libraries, you can write code that is safe and reliable in multi-threaded, interrupt-driven, and signal-handling environments. Always carefully consider the reentrancy requirements of your code, especially in systems where concurrency is present. Always strive to write the simplest, most straightforward code possible, as this will often lead to fewer reentrancy issues. Use the available tools to help you detect and fix concurrency problems.